What I explained about Hough Transform so far is not enough to implement it. And the reason is because the number of possible slopes and intercepts for a given edge points is actually infinity. So we cannot implement that. What we have to do is just to discretize that AB space. So we can, for example, divide A into k increments, let's say 9, and what we would get is also k increments for B. And by increment I mean just the number of possible values. Okay, so for that reason I prepared myself this grid of the AB space. So what I have here is an A-axis that is divided on k possible values, and k in this case is equal to 9. And obviously I would get also 9 possible values for B. So the maximum value here is 8 because I'm starting from 0. Okay, so initially this AB space is set to 0. So each of these cells has to take, after the final process, a given value, and I'm going to explain that in a moment. So initially they are all set to 0. And in order to fill, to associate values with these cells, we have to go back to our equation of B, the equation of aligning the AB space. So B is equal to minus x. So x is the x-coordinate of a given edge point I, okay, multiplied by A plus YA. Now what we do is for a given edge point, for example, I'm gonna do that for the point P0 to get this line on the discretized AB space. So what I have to do is just to take the coordinates of that edge point, which are x0 and y0, and plug them in this equation. So I get minus x0 a plus y0. Good. So x0 is known, y0 is known, and what I should do next is to evaluate all the possible values of B for, the value of B for all the possible values of A. So we start from A equal to 0, replace that in this equation, and get B, because we already have x0 and y0, they are known. For example, let's say that for A equal 3, the evaluated value is B equal 3.2. Okay, so what I should do first is to round this value to the nearest possible value. So by rounding this value, I'm going to get B equal to 3. And this is associated, of course, with A equal to 3. And then go and look for the coordinates 3, 3. This is the coordinate 3, 3. This is the associated cell, corresponding cell. And as I said in the beginning, all these cells are set to 0. So what I have to do here is to increment the value of that cell. And what I'm going to get is 1. Okay? So if I do that for all possible values of A, I would get a line that is diagonal in this way. And this line can be represented by a set of increments in this diagonal way. So what I have to do is just to increment the cells in this direction. So for the point P0, this is what I get for my discretized AB space. I'm going to do the same process for L1. So L1 is going to be a horizontal line. So it can be, for example, something like this: 1, 1, 1, 1. And once I get here, I have to increment this value, even if it's already incremented. So if I increment that, I will get 2 and 1s in the next cells. Similarly, for this line L2, I would get 1, 1, 1, 1, and once I get here, I have to increment that again to get 3 and get 1s for the rest of diagonal cells. So this is the reason why this is called an accumulator, a Hough accumulator. Hough accumulator. Because we are accumulating votes of lines that have slopes and intercepts A and B. So now everything else is of course set to 0. All the other cells that are not marked have a value of 0. So one thing that I can say is if a given slope and intercept, that is a line, has an accumulation that is higher or equal than 3, so this is my threshold, then take this this line as a detected line. So in this case, I would get this cell, and this cell is corresponds to the value of 4 for A and to the value of 4 for B. Okay, so the line that I would have detected is given by y equal 4x plus 4, and I should plot this line on this x and y space, and this line would be just this one. Okay, so this line would have a slope of 4 and an intercept of 4. Now, let me discuss the effect of the number of increments. So here, I've chosen just k, just for the sake of simplicity to explain how this works to you. But in practice, we do not choose a value that is as small as this one. Otherwise, the lines that we would detect would be a mess. So for example, in this case, for k equal to 9, the points that would be considered as collinear would be scattered, would be like this, for example, just because we do not have enough accuracy to detect the collinearity of these points and say, well, they are a line. So in order to increase the accuracy of that, we have just to increase the number of increments and say, for example, k equal to 1000. So in this case, the points that would be detected as collinear would be less scattered than this case. But we have to be, of course, careful not to choose a big value for k, because we would just lose more computational time for nothing. Now, finally, one thing that I would like to mention is to explain why this method is actually a global method. Well, it is called global because we are evaluating collinearity of points on the entire image, on a global scale, not only on a given neighborhood as we did for the local method.